Welcome to the second part. I'm gonna call this 3-7 because 3-6 is dead to me. Anyways, no. We're going to take a look at the gradient vector in this lesson. So let's start. What's a gradient vector? Gradient vector is denoted with an upside down triangle like this, del, and it has all of the partial derivatives of each independent variable with respect to the dependent variable. So f sub x, f sub y, f sub z. And it represents the direction of fastest increase at the point xy for 2 input, xyz for 3 input, xyzt for 4 input, etc., etc., etc. Now let's get straight into an example. Find the gradient. Actually, first of all, I'll address how later, but let's get straight into an example. Find the gradient. So we write something like this: z of xy, or just z, is equal to 2x. It's a vector. This is a vector. This is important. It's a vector, not a scalar. Vector, not a scalar. I should have bolded it, but I didn't. So what does this mean? Find the direction of fastest increase. This is pretty easy. Just plug in. I could write z of 1, 1 is 2, negative 2. So at 1, 1, which means z will be 0, so at something like 1, 1, at right here, the fastest increase, the direction of fastest increase will be at 2, negative 2. So 2 on the x-axis, something like this, negative 2 on the y-axis, something like, so like this. So it's this direction, which makes sense because it's going, you know, up, and then this Pringle is going up, so that makes sense. The hyperbolic paraboloid is going to increase fastest when you go that direction. Let's find the gradient at 3, 2 is 6, negative 4. Also makes sense because 3, 2 will get you a height of 5, so 3, 2, something like right here, it's pretty high. And the direction of fastest increase will also be in this direction because it wants to go higher. 4, negative 1. 4, negative 1 is what? 4, negative 1 is 8, 2. So 4, probably like right here, negative 1. So it's probably pretty high, like right here, or something like that. Where is it trying to go? It's trying to go 8, or in the x direction a lot, and then a little bit in the y direction, so something like this. So it's trying to go in this direction if you just look at the plane, which means it's going to go up. It's going to go up a lot, right? That's the direction of fastest increase. Makes sense. The origin. What is the gradient at 0, 0? The gradient at 0, 0 is 0, 0. Now what does that mean? That means there is no direction of fastest increase. If we go, or there's more than one direction of fastest increase. No, or more than one. So in this case, if you go up this way, direction of fastest increase is this way. If you go up this way, that's also a direction of fastest increase. So both ways that you go are directions of fastest increase. So since there's more than one direction of fastest increase, there isn't a direction vector, or there isn't a vector for it. So that's an application of how to use it. So why does it work? Now I explained the pretty convoluted. I think this explanation is pretty convoluted as well. I think it will make more sense when we get to the next part of this lesson, the level curves, level surfaces. But why does it work? So let's say we're just going to focus on f sub x and x. You could apply the same argument for y, f sub y and x, f sub y and y, right? F sub x and x. So if your f sub x has a positive sign, for example 2x right here, if your f sub x has a positive sign, then we're increasing when x is greater than 0, right? So if we're increasing when x is greater than 0, what we want is to go to the direction where it's increasing. So it's going to go away from origin, or away from origin to x-axis, right? So it's going to go away from the origin, which in this case, yes, it does. It goes away from the origin to x-axis, right? The direction of fastest increase, if you go farther and farther, it goes away from the origin, because the gradient is 2x. Now, what about if f sub x has a negative sign? If f sub x, or if your x is negative, if your x is negative, or if f sub x is negative, and your x is greater than 0, then the result that you're going to get, the resultant vector that you're going to get is, let's say x is 4, for example. So if x is equal to 4, your resultant vector that you're going to get is something negative, and then like whatever, we don't care about this, but it's something negative on the x direction. So that means it wants you to return back, right? If it's negative, it's getting more and more negative, like negative 2x, for example, then it wants you to return back for that direction of fastest increase, right? Because you're not going to increase if you go in the direction where it's decreasing. So this is towards x-axis, or towards origin, right? We could apply a similar argument for f sub x with a positive sign and x is less than 0. So if x is less than 0, let's say x is like negative 5 right here. If x is negative 5, then what you get for the direction vector, what you get for the gradient, not the direction vector, I'm sorry, the gradient is, we want to go more and more negative, right? It'll be negative 10. So if x is negative 5, it'll want to go in the direction of negative 10, which is very, very negative. And why does it want to go in the direction of negative 10? Because it wants to increase more. That's why it's a direction of fastest increase. So this also goes away from origin. If f sub x is negative, if f sub x is negative and x is less than 0, right? I should say this is like toward negative, toward positive, or it's like moving positively towards, this is going towards the origin for positive, so it's going towards the negative side, and then this is going towards, you guessed it, the positive side. Because let's say if we have x is equal to 4, or x is equal to negative 4, and we have f sub x having a negative sign, then we get the gradient of f is positive, which means it wants to go to the positive direction. Because if you go in the negative direction, if you go more and more negative, it's just going to be decreasing, more and more decreasing. And you don't want to go in the direction of decreasing, you want to go into the direction where it increases. So this goes towards the origin. So that is my explanation right there. Now that probably won't satisfy. You can apply the same logic for y, f sub y, and f sub x, but if there's combinations, it gets a little bit more convoluted. Now, I hope this explains it, but what we're going to do is, first of all, we'll do this, but what we're going to do is we'll do some level curves, and then I hope that clears it up a little bit. So what are some relationships between the directional derivative and the gradient vector, right? So first of all, we already said this, we already established this in the previous video, is the directional derivative in the direction of u is equal to, or the unit vector u, is equal to the dot product between the gradient vector, which I don't need to have a hat right here, I mean I could, but the gradient vector of f at xy dot product with u. And if u is in the direction of the gradient, if the unit vector is in the direction of the gradient, then the derivative is maximized. Why? It goes back to very, very like basic principles of the fact that the dot product is equal to the magnitude of del f times u times the cosine of theta. And if theta is 0, which means they're in the direction, so your del f and your u would be in the same direction. Let me draw it. Then what would happen is the cosine clears, and what you get is just the magnitude of f. So the derivative is exactly equal to the gradient vector, or the magnitude of the gradient vector, not the gradient vector. The derivative is exactly equal to the magnitude of the gradient vector if the derivative is in the same direction as the gradient vector, or the unit vector that you used to take the direction of your derivative is in the same direction as gradient vector. What about if they're perpendicular? Well, if they're perpendicular, then what's the angle? What's the cosine of the angle? The angle is 90 degrees. So theta is 90. So what does that mean? That actually means that cosine will be 0. Cosine of 90 is 0, so it's 0. So there is no change. No change in the direction, or no change in the derivative at all. Right? And when you have no change in something, you call that constant. Right? And where in this chapter have we learned about stuff that's constant? It's in the level curves. All of the curves in, or I probably should draw it later. All of the curves have constant value. It's just a curve, right? It's like a ring of places with constant values, or a region of places with or not a region, but all the points on that line, all the points on that curve have constant values. And so what you end up getting is when you walk along a level curve, or when you take a direction that's tangent to a level curve, your derivative is 0. Which kind of makes sense. It kind of makes sense. So if I draw something like the elliptic paraboloid, bad drawing. If I draw something like this elliptic paraboloid right here, right? Its level curves are like circles, right? Or ellipsoids, or ellipses. I'm sorry, not ellipsoids. And their tangent plane. I'm just gonna put a tangent plane right now. So tangent plane is like this. The direction of fastest increase right here, right? That kind of aligns with a tangent plane. The direction of fastest increase aligns with their tangent plane. Is like up here. But then the direction where they don't move at all, these two directions right here, not like the directions where it's perpendicular to the gradient vector, you can see that on the tangent plane they also don't move at all. Right? This is a bad drawing. I can draw better in a bigger screen. If you guys want me to do that, put in the comments. But it's not moving at all in the z coordinate, right? The z coordinate was what we care about. So if we have like a bunch of these tangent planes all around the paraboloids, what you end up getting is you get a circle, a contour of point where when you put a tangent plane in it and you move in that direction of the tangent plane, you don't move in the tangent plane. You also don't move in the ellipsoid itself. Right, so that's a little bit of a weird concept to think about, because that doesn't appear in single variable calculus. There isn't another direction to move in single variable calculus, but that's what we're gonna have to get used to. But anyways, let's do an example. So fxy is equal to this. Find the rate of change of f at p is 0 in the direction p to q 1, 2. So we'll just do this regularly. This is kind of a review of last time. F sub x is what? Simple, e to the y. F sub y is what? Simple, x e to the y. And what's the direction? The direction is p to q. So let's calculate the vector pq. Pq is what? Is 1 minus 2 is negative 1. And then 0, 2, and 2 minus 0 is 2. So that's the direction. Now, we don't really want that though. What we want more is a unit vector. Let's use a unit vector. Let's do it like this. Right, so unit vector, what's the unit vector? Unit vector is divide that with that. What will that get you? That will get you negative 1, 2 on top, over square root of 1 squared plus 2 squared, which is exactly 1/5. This is annoying. This is seriously annoying. Okay, I don't care anymore. 1/5, or 1 over square root of 5 times negative 1, 2. Right, so we got our gradient vector and we got our directional derivative. So now what do we do? Now let's evaluate the gradient vector. Okay, so evaluate the gradient vector at the point P20. So what is the gradient vector at the point P20? Well, let's plug it in. Gradient of f at 20 is equal to f sub x first, e to the 0 is 1, and then 2 times e to the 0 is 2. So it's 1 comma 2. 1 comma 2. So finally, the derivative in the direction of 1 over square root 5 times negative 1, 2 of f of x, y, so f of 20 is equal to 1 over square root of 5 times negative 1, 2 dot product with 1, 2, which will get you what? This will get you negative 1 times 1 is negative 1. And then, so 1 over square root of 5. Negative 1 times 1 is negative 1. And 2 times 2 is 4. So negative 1 plus 4, which is 3 over square root of 5. That's your derivative. Now, in what direction is the derivative maximized? Oh gosh, my parents are being really noisy. In which direction is the derivative maximized? The derivative is maximized in the direction where the gradient vector is in the direction of the derivative, or the unit vector is in the direction of the gradient vector. So how are we going to get that? Gradient vector is at 1, 2, right? So in which direction is the derivative maximized? We just need to take the unit vector of the gradient vector. So the unit vector of the gradient vector is equal to the gradient vector divided by the magnitude of the gradient vector, which is, well, this is 1 over square root of 5 again. 1, 2. So in that direction, the derivative is maximized. Very simple. Just use a unit vector and you will get your loot. Now, what's a level curve? We've reviewed level curves already. We've done level curves already in the first episode, but we're going to review, in the first episode of this chapter, but we're going to review them. So level curves is when you set a function like this. This is a hyperbolic parabola right here, equal to a constant, k or c, right? And then we evaluate each constant, like in each scenario, how it works. So what you're going to get is you're going to get something like x squared minus y squared is equal to 1. So at k is equal to 1, we have x-intercept of 1, and we have hyperboloids. So that's at k is equal to 1. Like that. We can graph them like that. At k is equal to 2, or at k is equal to 4, I should say, we can graph the hyperbolic paraboloids. Or no, we can graph the paraboloids. These look pretty paraboloidy. They don't really look very hyperboloidy. I'm not very good at drawing them, so something like that. And then, yeah, that's at k is equal to 4. Right, k is equal to 1, we have these. K is equal to 4, we have these. Those are level curves, right? Now, let's put the claim that I have, where is it? If u is perpendicular to the direction of the gradient, then the level curve and the, or no, not the level curve, I'm sorry, the derivative is maximized, right? So if the derivative is maximized, like let's say we're going here, so where would the derivative be maximized? It'd probably be like somewhere here, right? Because we're moving positive, we're moving from k equal 1 to k equal 4, right? If we're here, the derivative is probably maximized when we're moving here. We want to get closer and closer to the x-axis, as close to the x-axis as much as possible. It's basically delineated by the thing that we worked out previously is 2x negative 2y. So if we move closer and closer to the x-axis, we get the direction of fastest increase. Right, so what does that mean? If u is perpendicular to the direction of the gradient, so if the unit vector is perpendicular to the direction of the gradient, what happens? Well, we get 0, because well, if it's perpendicular to the direction of the gradient, first of all, what happens when u is parallel to the direction of the gradient, or in the direction of the gradient? It's maximized. The derivative is maximized. Now, if it's parallel to the direction of the gradient, and the gradient is the direction of fastest increase, then isn't the gradient perpendicular to level curves? Isn't the gradient perpendicular to the level curves? Right? So the direction of fastest increase is perpendicular to the level curves, right? Because theta in the direction of fastest increase is 0, but theta in the direction where there's no increase, where it's constant, is 90 degrees. So what we find out is actually the fact that the gradient is perpendicular to level curves. The gradient is perpendicular to level curves. And this idea also persists for 3 variables. Gradient is also perpendicular to level surfaces. The gradient is perpendicular to level curves, and the gradient is perpendicular to level surfaces. Now, how can we use these two facts? Right? First of all, you can use a contour plot. You can see a contour plot, and then you can kind of trace the direction where a vector would go. So it will be something like, wait, no, let me insert a new page after this page. So it'd be something like, if you had like level surfaces like this, and then 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 like this. Let me close them. Right, if you had level surfaces like this, and let's say this is like velocity or something, and let's say this is higher, so this is like k equals or k equals 4. Let's say this k equals 4, that's k equals 3, k equals 2, or like f equals 2, k equals 1, right? So you can trace the direction that these guys would go if they want to go from a lower maybe let's say potential, lower potential to a higher potential, you can say it's no, it's not going to be like that. It's going to be perpendicular right here. It's going to be perpendicular right there. It's going to be perpendicular right there. Right? So perpendicular, perpendicular, perpendicular. Right? And you can predict the direction it's going to go after the level surface as well. What about right here? It's going to go perpendicular right there. Okay, let me draw in. That's not very good. Perpendicular right there, and then perpendicular right there. See? You can trace these level paths. You can trace the direction that these particles are going to go because you know that it's always perpendicular to the level curve. That's where they want to go. Right? It's very useful in electricity, magnetism. It's also pretty useful in like climbing a mountain as well. If you climb a mountain, you don't want to be in a direction of fastest increase every single time, or you will have a very, very bad time. So, or maybe you do, I don't know. Maybe you don't want to climb like mellowly and then have a really steep curve right at the very end. Maybe you do, I don't know. But that's what we know. We know that the direction of fastest increase is always perpendicular to the level surface. And it makes sense for tangent planes as well. In fact, it makes the reason why we're going to use this to predict, or no, not predict, but we're going to use this to find a tangent plane to a level surface. The level surfaces are not level curves. Level surfaces are different than level curves. In fact, I'm going to open a new flip. I'm going to open a flip chart from 3.1. And where is the level surface that I drew? Right here, right? These are level surfaces. And level surfaces act the same. It's just in x, y, and z, sometimes defined implicitly. X, y, and z in terms of a constant k, k or c, yeah. Okay, I'm sorry, something happened. So let's do our example. Find the tangent plane at 1, -2, and 2 of x squared plus y squared plus z squared equals 9. There's two methods. One way you should already know, and the other way we're going to do. So the first method is x squared plus y squared plus z squared is equal to 9. We can solve for z. Z is equal to square root of 9 minus x squared minus y squared. Usually that would be plus or minus, but since z is positive in our point that we want to find, it has to be positive. Yeah, that's unfortunate. So what's z sub x? Z sub x is the derivative, and then you have to do the chain rule. So it's negative 2x over the square root, or 2 times the square root of 9 minus x squared minus y squared. Z sub y is the same thing, negative 2y over 2 times the square root of 9 minus x squared minus y squared. So what is z sub x at the point that we want? Z sub x at the point that we want is 1 on top. You'll get 1 on top, or negative 2 on top, but we can cancel. So just cancel, 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 cancel. You'll get negative 1 on top, and then you'll get 9 minus 1 minus 4, which is 1, 2. So 9 minus 1 minus 4 is 4. Square root of 4 is 2. So it's negative 1 over 2. Z sub y is the same. Z sub y, or no, not the same, I'm sorry. And negative 2 is 2, and the bottom will get you 2, so it's 1. So our equation is z minus 2 is equal to negative 1/2 times x minus 1 plus 1 times y minus 2. Or y plus 2, I'm sorry, y plus 2. So what about method 2? How do we find method 2? Well, we did talk about the gradient vector, the gradient of f being perpendicular to the level surface. So if the gradient of f is perpendicular to the level surface, how can we get a tangent plane for the level surface? The tangent plane to a level surface, what do you need for a plane? You need a point, right? And you need a normal vector. You need a vector that is normal to the point, normal to the plane. So a vector that is normal to a plane, won't that just be the gradient vector? Right? Because the gradient vector is always perpendicular to level surfaces, so it's always perpendicular to every single point in that surface, so it serves as the perfect perpendicular vector to a plane. So that means that the gradient of f is equal to 2x, 2y, 2z. So the gradient of f at 1, -2, 2 is 2, -4, 4. Now, how does it work? Well, this is our gradient vector, that's our normal vector. Gradient vector, normal vector, they're the same thing because gradient vectors are perpendicular to level surfaces. 2 times x minus 1 plus, or no, minus 4 times, and then plus 4 times. So 4 times y plus 2 plus 4 times z minus 2, I think. Yeah, 4 times z minus 2. What will that get you? Or are these two are the same? So this has to be equal to 0. Are these two equations the same is what we really want to find out. So are they the same? Let's find out. Let's move this here, and let's move this here. This is just a verification of the methods that we're using. See if they're actually accurate or not. Z minus 2, first of all let's simplify both equations. So we'll have z, x, and y stuff. We'll distribute it. Z minus 2 is equal to -1/2 times x plus 1/2 plus y plus 2. Right, I'm just going to be really quick. 1/2 and 2 is 5/2. Subtract it, you'll get 9 over 2. -9 over 2. And then subtract the z from the other side. 1/2 x plus y, and then minus z. We do want to multiply it by 2, however, because we want this side to be positive, or multiply by -2, in fact, because we want this side to be positive. So what we end up is getting 9 equal to x plus, or x minus 2y, because we're multiplying by -2, x minus 2y, and then plus 2z. So does that sound reasonable? Well, let's see. 2x minus 2 minus 4y minus 8 plus 4z minus 8 is 0. 2x minus 4y plus 4z is 0, not 0. Minus 2 minus 8 minus 8, 18. So x minus 2y plus 2z is 9. They match. They are the same. And that's the perfect ending to today's lesson. I will see you guys next time for maximization optimization.